Hello, my name is Dr. Jacob Hudis, and in this presentation I will be solving 3 problems involving emotional EMF. EMF stands for electromotive force. I'm a firm believer that the best way to learn physics is by solving problems. So let's do this. Here's problem 1. The problems get a little bit harder as we move on, and problem 3 involves calculus. A 0.4 volt potential difference appears across a 0.3 meter long wire as it moves through a magnetic field that is perpendicular to the plane of the screen. Determine the magnitude and direction into or out of the page of the magnetic field. You may want to pause the video because I'm going to solve the problem on the next slide.
Good morning,
The first part of the problem asks us to find the direction of the magnetic field. In order to do this, we have to use the Lorentz force. The Lorentz force is Q V cross B. This is a cross product, so this involves the cross product right-hand rule. There's more than one right-hand rule, so I like to call this one the cross product right-hand rule. To do the right-hand rule cross product, you take your right hand, you take these 4 fingers on your right hand, and you put them in the direction of the first vector in the cross product. In this case, the first vector in the cross product is V, so you take your fingers and you point them downward, and you have to curl your fingers in such a way that your thumb will point in the direction of the force on the positive charges. In this problem, the force on the positive charges has to point to the left. Therefore, the magnetic field must be out of the page, because if your fingers curl out of the page, your thumb will point in the direction of the force on the positive charges, or the opposite direction of the force on the negative charges. If you put your fingers in the opposite direction, and then if you curl them into the page, which would say the magnetic field is into the page, that would say that the force on the positive charges is to the right. But for this problem, that's not the case. The positive charges are on the left, and the negative charges are on the right.
Fantastic.
Now we know the direction of the magnetic field. The question also asks us to find the magnitude of the magnetic field. Inside the wire, the electric force is balanced by the magnetic force. That's the reason the charges stay separated. The electric force pulls the charges together, and the magnetic force pushes the charges apart. The electric force is always given by Q times E, where E is the electric field inside the wire. The electric field points from the positive to the negative, and the Lorentz force, or the magnetic force, is equal to QV cross B. In this case, it's just QVB, because the magnetic field and the velocity are at a 90-degree angle to each other. We can divide both sides by Q. The electric field is equal to the velocity times the magnetic field. The change in potential, or the voltage between the 2 sides of the wire, is equal to E times L. The voltage is always equal to negative the integral of E dot dl, and in this case, the electric field is constant, so it's just E times L, where L is the length of the wire. We can replace E with V times B, and that tells us that the change in potential between the 2 sides of the wire is equal to the velocity times the magnetic field times the length of the wire. The question asks us to find the magnetic field B, so we can divide both sides of the equation by the velocity times the length, and this gives us a formula for the magnetic field B. B is equal to the potential difference between the 2 sides of the wire divided by the velocity times L. These numbers were given in the problem. We plug in the numbers, and we find that the magnetic field is equal to 0.267 Tesla. This is a relatively large magnetic field. The units for magnetic field are Tesla, named after the overpriced electric car that Elon Musk created, and Nikola Tesla, the famous scientist, was also named after that car. And that's the answer to the problem. And now we move on to problem number 2. In the diagram to the right, a metal rod with 0 resistance is pushed away from a 2 ohm resistor at a constant speed of 0.5 meters per second. The magnetic field in the region has a strength of 0.5 Tesla. This is the diagram. There's an applied force pushing this rod to the right. It's in a region of a magnetic field. The rod is moving with some velocity V. There's a magnetic drag force pushing to the left, and there's going to be some current in the circuit. The questions are A, determine the direction and magnitude of the induced current. B, what is the magnitude of the applied force? This is the applied force. And C, what is the power supplied by the pushing force, and what is the power dissipated in the resistor? I'm going to solve this problem on the next few slides. You may want to pause the video and try it on your own. Here's a solution to part A. The metal bar, and thus the charges in it, move to the right while the magnetic field points into the page. Applying the cross product right-hand rule, the force on the positive charges is directed upward, indicating a counterclockwise current flow. Ohm's law tells us that current is equal to voltage divided by resistance. In this case, the voltage is the EMF, it's the motional EMF, produced by the work done by the Lorentz force. In problem number 1, we showed that the voltage between the two sides of the rod was VBL, where V is velocity, B is magnetic field, and L is the length of the rod. Therefore, the current flowing in the circuit is VLB divided by R, where R is the resistance of the resistor. The current is 0.025 volts divided by the 2 ohm resistor, and that gives us a current of 1.25 times 10 to the negative 2 amperes. Part B asks us to find the magnitude of the applied force. This is the applied force pulling the rod to the right. The Lorentz force moves the charges upward along the wire, creating a current. This current flowing through the magnetic field creates a drag force. This is the magnetic drag force. The magnetic drag force is just another application of the Lorentz force. It's equal to I, L cross B, and this is equal to IL times B. The current is BVL over R, so I can replace the current in this equation with this formula. The magnetic force is equal to ILB, that's BVL over R times LB, and this is a formula for the magnetic force, B squared L squared times the velocity divided by R. This is moving at a constant velocity, which means the net force on the rod has to be equal to 0. Therefore, the force of the push has to equal to the magnetic force, and this is equal to B squared L squared V over R, and we can plug in the values, and we can solve for the force of the push, which is equal to 6.25 times 10 to the negative 4 newtons. The final part of the problem asks for the power supplied by the pushing force and the power dissipated in the resistor. Well, we know the formula for the current, and power in a resistor is equal to I squared times R. So the power dissipated in the resistor is I squared multiplied by R, and that's this formula, B squared V squared L squared divided by R. The power, or work per unit time, supplied by the pushing force is equal to the force dotted into the velocity. This is the formula for mechanical power. The pushing force multiplied by velocity is equal to B squared V squared L squared over R, and as you notice, the power of the push is equal to the power of the resistor. The key idea here is energy conservation. The power supplied by the applied force is equal to the power dissipated in the resistor. This means that all the work done by the applied force to keep the wire moving at a constant speed is transferred into electrical energy, which is then dissipated as heat in the resistor. And here's the third and final problem.
This ought to be intriguing.
A metal rod of length L, shown in the diagram, is moving at a constant speed V, parallel to a straight wire that carries a steady current. The separation between the rod and the current-carrying wire is Y. Derive an expression for the potential difference that develops between the two ends of the moving rod. Here's the setup. There's a wire with a constant current in it. A distance Y from the wire is a rod, and the rod is moving at a velocity V. And the question is, what is the potential difference between the two ends of this rod? You may want to pause the video, because I'm going to solve this problem on the next slide. We've already seen that the electric field inside the rod is equal to the velocity times the magnetic field. In this case, the magnetic field created by a current-carrying wire is mu naught I divided by 2 pi x, where x is the perpendicular distance from the rod to any point in space. This tells us that the electric field is equal to the velocity times mu naught I divided by 2 pi x. The electric field is a vector. The change in potential between any 2 points is negative the integral of the electric field dot dl. In this case, we have to integrate from y to y plus L, where L is the length of the rod. Everything here is a constant except for the terms with x. So all the constants can come out of the integral. Then we take the integral from y to y plus L of dx over x, and that gives us this formula. The change in potential between the two sides of the rod is equal to negative the velocity of the rod times mu naught I divided by 2 pi times the natural log of y plus L divided by y, because the integral of 1 over x is equal to the natural log of x. This tells us that the electric field inside this rod is not constant. And the reason it's not constant is because the magnetic field from a current-carrying wire is not constant. It's stronger when you're closer to the wire, and it gets weaker as you move farther away from the wire. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis.